Hello everyone and welcome to this video dealing with approximating a definite integral using numerical integration techniques. The objectives for this video are 1. Approximate definite integrals using trapezoid rule. Number 2. Approximate definite integrals using Simpson's rule. And number 3, analyze the approximate errors of the trapezoid and Simpson's rule. The key difference between these two. Number 1, the trapezoid rule uses trapezoids. We're going to do it very similar to when we would approximate a definite integral involving a rectangle. Now we're going to use the trapezoid to do it. So we'll find the areas of each individual trapezoid. Simpson's rule goes into basically the idea is, why are we approximating the area between a curve and the x-axis by using a geometric figure when we could use another curve? And so Simpson's rule uses quadratics to help us approximate those. So let's take a look at the development and the use of both of these. The first thing I want you to do is we'll look at the trapezoid rule. And what you have to recall, you need to recall that the area of a trapezoid is 1/2 the height times the sum of the two bases. Okay. Now, the thing that happens on these things when you're working on these, remember the height is always the length of a segment that is perpendicular to the two bases. In a trapezoid, the two bases are the parallel sides. So, in essence, when we look at these, what happens is that I went through and I've divided this up into an interval, and the idea that we want to have here is that this is a regular partition, so that the distance between all the x's should be the same. So this was my attempt. It's close, but obviously there's a little bit of difference there. But our idea on this one is that delta x, that the difference between any two consecutive x values is going to be the same. Delta x is constant in these problems. And delta x will represent the height of the trapezoid, because that is going to be the length of the segment between the two parallel sides. The parallel sides are the vertical segments that are at each different x value. And remember, the height of those, by definition, the length, the distance, or the y-coordinate of a point tells me the distance between the x-axis and that point. And so the length of each base is equal to the y-coordinate that we have at that point. So in this particular function, if this function is y equals f of x, I can go through and find the area of each trapezoid. So I've gone through, I've drawn in the lines, and then I've drawn in these light blue, the greenish lines, and those represent the fourth side of the trapezoid. And so I can go through and calculate the area of each trapezoid. So area 1, the area of trapezoid 1 is going to be 1/2 times delta x times the sum of the length of the two bases. Well, that's going to be, in this case, is at a, which I've called x0, and this one is at x1. So it's going to end up equaling f of x0 plus f of x1. Area 2 is going to be 1/2 times delta x times the sum of its two bases, which happens to be f of x1 plus f of x2. Area 3 is going to be 1/2 times delta x times f of x2 plus f of x3. And area 4 comes out to be 1/2 delta x times f of x3 plus f of x4. And then I can go through and add these up. Now, since I've set this up where the idea is that delta x is constant, if delta x was not constant, then you'd have to just calculate each one of these areas individually and then add them up. But if delta x is constant, then we have what's called the trapezoid rule. And that rule states that we're going to go and let f of x be continuous on the interval for the closed interval from a to b. The trapezoid rule for approximating the integral from a to b of f of x, should have the dx there, is that the integral from a to b of f of x dx equals 1/2 times b minus a over n, which that is, because we're going to use n as the number of trapezoids that we're going to use. So b minus a over n is delta x of the y coordinates. The f of x sub 0 plus 2 times f of x sub 1, which would be y1, plus 2 times f of x sub 2, which would be y2, and so forth, down to where we add y sub n. Or if you want 1/2 times delta x times y0 plus 2y1 plus 2y2 plus 2y3 plus, that continues to be 2y sub n minus 1 plus y sub n. And that represents the trapezoid rule. And we can use that. So if this way works with you can work with this with an equation or a table of values. And we can go through as long as delta x is constant. If delta x is not constant, then we cannot use this, and we'd have to, if we're going to use approximate the area using trapezoids, we would have to find the area of each individual trapezoid separately and add them up. But if delta x is constant, then I am able to use this trapezoid rule. So let's look at a problem here. I'm going to approximate the integral from 0 to 2 of 1 over x plus 1 dx, and I'm going to use 4 trapezoids. So in this case, the first thing I want to do is find delta x, and delta x is going to be b minus a over n, so it's going to be 2 minus 0 over 4, which is 1/2. And so at this point, I'm making a table of values. Okay, I know that my x values are starting at 0 and they're going to go up by 1/2. So I have those values. When I plug these values in for x into the original function, I get these results right here. And so now what I'm going to do is when I have a table of values like this, I like to just go through and expand it. And the one thing I have to do is I have to identify each value's factor. Now, if you remember in the trapezoid rule, it was going to be 1/2 times delta x times y0 plus 2y1 plus 2y2, and that continued on like that until we got to y sub n, the last one. The one thing I want you to recognize on this one is that the factors, if you will, on each one of these terms, the first and last value have a factor of 1, and everything else is a factor of 2. So when I write this out, my factors are going to be, for the first one, it's going to be 1, and then all the others, it's 2 until I get to the last one. And so what I'm going to do is I'm going to go and multiply each value with its factor. So each y coordinate with its factor. So it's going to I'm going to take that factor here times y. And so in the first one, I will get 1. Then I'll get 4/3, which would be 1.333. The next one, I'll get 1. And the next one, I'll get 4/5, which is going to be 0.8. And then the last one, I get 1/3, which is then 0.333. So now what I can do is I can add these up. When I add those up, that's going to be this value right here. So now when I add these particular values up, I will get 4.6667 is what it'll end up being. Okay, so that now represents this value. So to approximate the definite integral, I am going to go through and take 1/2 times my delta x, which is 1/2, times the 4.6667. And then when I do that, that comes out to be about equal to 1.11667. And that would end up being my approximate area between the curve and the x-axis from 0 to 2 for 1 over x plus 1. Now let's take a look at Simpson's rule. And to do Simpson's rule, to go through and really kind of get a feel for what's happening with Simpson's rule, we want to start out by looking at P of x equal to the general quadratic ax squared plus bx plus c. And we're going to use capital letters for the coefficients here because we're going to use because we have lowercase there. So the integral from a to b of P of x dx is going to be the antiderivative of that, which is ax cubed over 3 plus bx squared over 2 plus cx from a to b. And when I evaluate the definite integral and then rearrange the terms, this is what I get. Okay. Now, what happens on this is I'm going to go and pull out a common factor. And the common factor, I want to pull out a common factor so I don't have any fractions anymore. And my common factor in this case is going to be b minus a. So I need to go through and factor this. Now, if you don't recall that b minus a is going to factor as this, and there's a pattern that's associated with it. You can double check it, but this is going to be a times b minus a times b squared plus ab plus a squared over 3. This is a difference of two squares. And when I pull out a 6 times b minus a divided by 6, I will end up with 2 times capital A times this plus 3 times capital B times this plus 6c. Now, at this point, we start going through, we expand things, move things around, and combine things as best we can. And what's going to happen then is we're going to get this expression here, that we're going to get this thing when as I expand it, combine things around, I will get b minus a over 6 times capital A times little a squared plus capital B times little a plus c, which happens to be P of A, plus 4 times capital A times a plus b over 2 squared plus capital B times b plus a over 2 plus c, which happens to be 4 times P of a plus b over 2, and then capital A little b squared plus capital B times little b plus c, which happens to be P of B. Now, so this is the form. Now, there's a lot of algebra there. You can go through and try to expand it. It also is described in the book. So if you look at the Simpsons rule part, if you go to WebAssign and go pull up the ebook, you can see some of the calculations. But the end result is you get this. Now, the other thing I want you to recognize here, that this right there, that is the midpoint between A and B. Okay? That's the midpoint between A and B. And so that's going to come into play in terms of the formalization of this process. So now what I want you to do is I want you to keep in mind on here that delta x is the difference between two consecutive x's, and that is equal to b minus a over n. Okay? And so the thing I want you to recognize here is that when we're doing these, we're going to partition this thing into a regular partition. So the difference between consecutive x's is going to be the same. So if I look at the integral from x0 to x2, notice I have the distance between here is 2 times delta x. Okay, because I have I don't have the x1 in there. So this integral is going to be approximately equal to 1/6 times 2 delta x times p of x0 plus 4p of the x0 plus x2 over 2 plus p of x2. But remember, This is the midpoint. And since delta x is constant, and this point right there happens to be at x1. So I get 1/3 times delta x times p of x0 plus 4p of x1 plus p of x2. And that same thing happens when I look at x2 from x2, the integral from x2 to x4, that this becomes x3. So I have something in that form. And all the way down until I get to the very last one, x sub n minus 2 to x sub n, that this becomes, this one in the middle is the midpoint, which is x sub n minus 1. Now notice also what happens then when I go through and add these up. I have a common factor when I add all these things in red up. That is the 1/3 times delta x. That can be pulled out. Okay? And the other thing I want you to notice is that when I add this one here to this one, I will get 1/3 times delta x times p of x0 plus 4p of x1. But now with the p of x2, though, that's occurring twice. So I'll have 2p of x2 plus 4p of x3 plus p of x4. And that pattern will continue. So you're going to see the first one here will always have that factor of 1, and that will alternate. Let's formalize this in the next slide. So the formal way of looking at Simpson's rule is that the integral from a to b of f of x dx is going to be approximately equal to b minus a over 3n times the y0 plus 4y1 plus 2y2 plus 4y3 plus 2y sub n minus 2 plus 4y sub n minus 1 plus y sub n. Or in this way, 1/3 times delta x times that. And so the same thing happens when as we were working on before with this, what we did with the trapezoid rule, I'm also going to use with Simpson's rule. The only thing you have to realize on this is that we have to have an even number with Simpson's rule because of how you have to use the midpoint in there. We have to have an even number of subintervals, okay? Which means that in order to use Simpson's rule, we have to have an odd number of x values. So in this case, 1, 2, 3, 4, 5, 6, 7, 8. I have 9 values, so I'm okay. I have 8 subintervals. Okay, and so I can do this one doing the same process as we did before. What this one is looking at, this is looking at a pond. And so we're going to go through and find the area of the surface. We're going to approximate the area of the surface of the pond. And so we start at one end and we move 3 feet down. The pond happens to be exactly 24 feet long. And we're looking at measuring the distance in feet across the pond. So anyway, what happens on this one is I can go and I have that same idea, the factor that we did before. But this time, my factors start at 1. They start at 1, and then they alternate 4, 2, 4, 2, all the way down, and then it'll be 4 and then 1. So you'll know if you've set it up right, as long as you have a 1, 4 at the beginning, and the very end is a 1 and a 4, and it's just alternating between there, you're probably in good shape. So in this case, my factors are going to be 1 on the first one, then 4, 2, 4, 2, 4, 2, 4, and 1. And like we did before, we now need to go and multiply those. So I'm going to take y times my factor. I'll multiply those and add them up, and then we can go through and finish the problem. So go ahead right now, pause the video, multiply these things through, and when you come back, we'll finish this thing up. Okay, welcome back. When I went through and multiplied these out, these were the values that I came up with. Hopefully I did those. I didn't make any silly mistakes as I went through. I just tried double checking them again. But when I add all those up, I will get a value of 124.7. That comes up to be what I get when I add up all of these. And so using Simpson's rule to go through and approximate this definite integral, my integral in this case from 0 to 24 of my function, we'll just call it f of x dx, is going to be approximately equal to 1/3 times, now in this case, my delta x was 3 because I was going up by 3 every time, times the 124.7. So that equals 124.7 because 1/3 times 3 is going to be 1. So in this case, the approximate value of the definite integral is 124.7. And as I said, this was representing looking at approximating the area of a pond surface. So this would be the units on this, for this particular one, would happen to be square feet. Now, the other thing that's important to remember here, trapezoid rule and Simpson's rule, while they are decent approximations and sometimes they are necessary, because this would be something. The first function I did with the trapezoid rule, we could have integrated that one. We could have gone through the integration process, come up with the exact answer. But this particular one right here, I don't have a function. I just have my function is defined by a table of values, so I could approximate that definite integral using this. But also, if I had a situation where I was working with a function that I did not know the antiderivative for, and it didn't fit any other integration techniques that we have, then we could still go through and approximate the definite integral using Simpson's rule or the trapezoid rule. But the important thing to remember is these are approximations, and therefore, because they have their approximations, they do have an error associated with them. And as such, when we're working on these things, it's having a way to understand the error is going to be another thing that we have to work with. And so, this first one deals with the trapezoid rule. If f of x you have to have a continuous second derivative. If it's not continuous on that integral on the interval from a to b, then we really don't have much to help us with the error on this one. Then the error e in approximating our definite integral by using the trapezoid rule is going to be the absolute value of e is less than or equal to b minus a, that thing to the third power, over 12n squared, again, where n is the number of trapezoids you're working with, times the maximum of the second derivative of x on the interval from a to b. So you've got to identify what is that, the maximum value of that second derivative on an interval. Now, a lot of times it will end up being at an endpoint. Okay, but it is possible it could be someplace else. Sometimes it might be just a matter of understanding the type of function you're working with. Like if you're working with a trig function, your second derivative is a sine or cosine. Obviously, the maximum of that is going to be 1. Okay. If you're working with Simpson's rule, if f of x is in a continuous, but now we have to have a fourth derivative, and it really comes into play just because of the fact that we're working with a quadratic and the antiderivative is a cubic. So the fourth derivative is going to help us with that error. Then the error in approximating that integral from a to b of fx dx in Simpson's rule is that error, e, the absolute value of e, is less than or equal to b minus a to the fifth power over 180 n to the fourth, where n, again, is the number of parabolas you're using, and of number of intervals, and then maximum of the fourth derivative of f evaluated at x, where x is some value from a to b. Okay, so let's take a look at this one. So an example of this one, really kind of looking at what we just did. How many trapezoids would I have to have so that my error would be less than 0.01, 1/100th? Okay, so in this case, I went to the second derivative. My second derivative of this is 2 over x plus 1 to the third power. And so the maximum of my second derivative on the interval from 0 to 2 is going to happen when x is 1, or sorry, when x is 0. So when x is 0, I'm going to get 2 over 1 to the third, so I get a maximum value of 2. And so therefore, my error is going to be less than or equal to b minus a, so it's 2 minus 0 to the third power over 12n squared times 2. Which when I simplify that, that's going to be 16 over 12n squared, which reduces to 4 over 3n squared. And so what I need to do now is I just want to basically identify the value of n that's going to get me to where I am less than or equal to 0.01, where that's less than or equal to 0.01. So I just said 4 over 3n squared is less than or equal to 1 over 100. 0.01 is 1 over 100. And so 3n squared has to be 3n squared would have to be equal to 400. Solving that, that's going to happen when n is 11.55. So I would need 12 trapezoids. I did make a mistake on this in terms of notation. In reality, these should be right here. Let's just make these equal signs. Okay, and so this would be equal. And so since we got to something to 11.55, it would be 12. Technically, when I went through and solved these things, those should have been switched to greater than or equal to, because I really just flipped the fractions, took the reciprocals. But the end result is that in order for me to get an approximation that is with 1/100th of the actual value, I would need 12 trapezoids. I could do the same thing working with Simpson's rule, but obviously I'd have to go to the fourth derivative, and I would be using a different, the higher powers in that one, but the process would be the same. So with that, this does conclude this video. Make sure that you're comfortable with the setups, if you will, for trapezoid Simpson's rule. And when we are in class, we'll take a look at those again, and I'll show you another way in terms of going through and do it. I tend to use a table. If I have a table of values, I tend to use a table of values, but you can go and just fill it in as in the rule, and we'll show you that in class. So with that, I hope everybody's having a good time, and we will see you in our next class.